Hi, my name is Pralav Shetty, and I work at the Woodruff School of Mechanical Engineering at Georgia Institute of Technology. Today I'm going to tell you about my work on the in situ investigation of transformations in copper-intercalated bismuth telluride. Bismuth telluride is a thermoelectric material. It can be used to make several interesting devices like this thermoelectric generator shown here. When heat is applied to one side of such a device, charge carriers dissipate away from the hot side and move towards the cold side through a phenomenon called the Seebeck effect. This allows the conversion of thermal energy into useful electrical energy. The efficiency with which heat can be converted to electricity, as shown here, is a function of the operational temperature of the device, higher temperatures providing higher efficiencies. However, high temperatures also accelerate diffusive and reactive processes that may disrupt device functioning. Bismuth telluride is a layered material, much like graphite, and it can readily accommodate several intercalants, including zero-valent metals, into its van der Waals gap. Thus, our goal in this study was to understand how the presence of metals within the gap would influence the thermal stability and eventually the performance of such devices. This work aligns well with the CNMS nanoscale transformations research thrust that seeks to understand how matter transforms locally for nanofabrication applications. First, we synthesized platelets of bismuth telluride and heated them in situ inside a transmission electron microscope. Above 400 degrees Celsius, the platelets began to sublime along well-known crystallographic orientations, exposing new edge facets that were parallel to the original facets. Beyond the melting temperature of this material, the facets began to bow and the material evaporated rapidly, as shown on the rightmost figure. Next, we used a chemical process to intercalate large amounts of copper metal within the van der Waals gap of bismuth telluride. The presence of copper in the gap reduced both the sublimation temperature as well as the overall melting and thermal stability of this system. Additionally, as shown in the middle bottom image, alternating bright-dark moire fringes were seen in samples that had copper intercalated in them. These fringes are attributed to the reordering of copper within the van der Waals gap to lower energy configurations that's enabled by the higher temperatures provided. This ordering phenomenon can also be confirmed using selected area electron diffraction as shown in the top panel. Several superlattice reflections begin to emerge at temperatures between 200 and 300 degrees Celsius. In addition to lowering the sublimation temperature and displaying interesting ordering dynamics, the copper-intercalated bismuth telluride also transformed to copper telluride at the very edges of these crystals. Here is a scanning transmission electron microscope or STEM image of a crystal in the midst of its transformation. We were able to freeze this state of transformation by quenching the crystal rapidly. As shown here, the transformation region contains three distinct phases: copper telluride in green, copper intercalated bismuth telluride in yellow, and a bismuth-rich phase as shown in purple. Using fast Fourier transforms, selected area diffraction, as well as nanobeam diffraction, we were able to pinpoint the exact orientation relationship between the transformation product, which is copper telluride, and the original crystal, which is copper intercalated bismuth telluride. We hypothesized that the copper telluride is able to form low-energy crystal facets with the host lattice because of the close spacing of the tellurium sublattices in these two crystal structures. In conclusion, the presence of metal intercalants can significantly alter the thermal stability of the host lattice. In extreme cases, phase transformations can also occur, as shown here in the phase transformation of copper intercalated bismuth telluride to copper telluride. These transformations are not limited to the high vacuum conditions inside a TEM, but have been repeated ex situ in other environments as well. I thank you for your time and attention, and I hope you enjoyed this presentation.